Okay, we asked the question, where does the graph of this function intersect the line? This is a parabola, this is a straight line. We can easily graph them. We can easily see where the point of intersection is. We graph the parabola by the usual means. Negative b over 2a, vertex, axis of symmetry, that's x equals 1. Plug that in, vertex is 1, negative 9. And the y-intercept is negative 7. X equals 0 gives you y equals negative 7. So we have this point, excuse me, the axis of symmetry. We see this as a graph of x squared, vertically stretched by factor 2, horizontally shifted 1 unit, vertically shifted 9 units down. Okay. For the straight line, we easily find the intercepts. The x-intercept occurs where y equals 0, and the y-intercept occurs where x equals 0. You have y equals x over 2 plus 4. If x equals 0, we see that y is 4. If y is 0, x is negative 8. Everybody seems to be doing okay with that idea. You just tend to maybe forget where you find the x and y-intercept. Two good ways a good way to graph the line, as long as the intercepts aren't real close to the origin. If they're real close to the origin, it gets difficult to see exactly, where the points are and how the straight line goes through. And if that's the case, you use any of a number of other possibilities, including the slope equals slope formulation. For example, find the y-intercept. And realize that the slope is 1/2, and move over some distance and up half that distance, and you get another point on the line. Or just substitute two values of x not too close together, and you can get the graph. Now you need to know all those ways of finding a straight line or recognizing a straight line when you see it, constructing a straight line, but for drawing the two graphs, any of those things will work. Then we get 2 points of intersection. We estimate the coordinates of those points. I just made my estimates. Notice that this is a pretty bad parabola I drew from here. No excuse. I wasn't trying to make it all that accurate because yours is not likely to be all that accurate either. Now you might well do better than I did. Many of you are making nice graphs, but we just need an approximate graph that gives us an approximate set of points of intersection to see if they make sense after we do the arithmetic or the algebra. Okay, so now, algebraically we find the point of intersection by setting these two expressions, the 2x squared minus 4x minus 7 and the x over 2 plus 4 equal. Easy to remember to do that if you know why. And the why is, well, the point of intersection is a point where both of these functions for the same x value give you the same y value. So this and this, therefore, at the point of intersection have to give you the same y value. So this has to be equal to this at the point of intersection. So we set this equal to this. Then we solve it. Okay, so now one thing that people still don't seem to be wanting to do, and it makes life so much simpler if you do it, is recognize denominators, and when you have a denominator, multiply through by the common denominator. And we do that. The only denominator is 2, so that is the common denominator in this case. And if you do a common denominator, it's best to do the least common denominator. It makes things just a little simpler notation-wise. But you could use any common denominator. It'll still work. But the least common denominator keeps things from getting too messy or any messier than they need to. Anyhow, we multiply both sides by 2. We get this. And then we take a look at what we have. If we haven't already done so, we recognize that we have a quadratic equation. And if we don't recognize that, then you're going to maybe want to subtract 8 from both sides and then see, well, here's x, and it's, oh, it's equal to a bunch of stuff with x. How are you going to deal with that? You can't isolate x. And then you go to magical thinking and do unjustified steps to torture this thing into some kind of a solution when what you have to do is recognize it as a quadratic equation. So here's the quadratic equation. Set that equal to 0, use the quadratic formula, you get two solutions. And then you plug each of these solutions into one of the two equations. Now, I plug it into this one because the arithmetic's going to be simpler. But we plug it in, and plugging into the equation y equals x over 4 plus 4, x equals 3.7, one of our approximate solutions, gives us this. It gives us approximately 4.9. So one of your points is 3.7, 4.9. How does that compare? Well, not all that great. We had 3, 8. Okay, well, 3 was a little low. If we went on 0.7 units further, this graph is pretty steep. Here it might well have gone up to 8, but that doesn't make any sense because it only goes up to 4.9 if you go beyond this point. So I don't know why I said that, but there it is. Okay, so bottom line, we didn't have a real good estimate here, but my graph wasn't very symmetric, so it's not surprising the estimate on the right-hand side wasn't very good. On the left-hand side, I think the estimate turns out a little better. We plug x equals -3/2 in because that was our estimate here. And did we get something close to 5/2? Well, not all that close, but it's not too bad. We plug in -3/2, we do the arithmetic, we get 3 5/8. Okay, that's about a little more than 3 1/2. 5/2 would be 2 1/2, so it's a little higher than I estimated. Okay, so that's how we do the intersection of two graphs. Now, the graphs aren't always linear and quadratic. You could have two quadratics, two linears. You could have a linear and an exponential, in which case the graph would be pretty much your only recourse. And even if you go to a graphing calculator, you're going to have to use graphical methods to zoom in on the point of intersection and all that stuff. Okay, well, anyhow, there we have it. And that just illustrates finding the intersection between the graphs of two functions.